This is AQA A-Level Chemistry. It's the Year 13 topic on aqueous chemistry, and this is video number 2 of 4. As always, I'm going to recommend that you pause, have a go at the activities for yourselves and see how you do. Get to find out what you might need to focus a little more on. So, in this video, we're going to carry on looking at acidity of metal aqua ions that we introduced in video number 1, but we're also going to look at some of the reactions that take place with them as well. So, if we take a look, we have got here acid and base reactions, N+2 and N+3 ions. We're going to see the differences between them. Now, we've looked at what's happened in video 1 simply when they're put into water. But here, we're going to think about what happens if we add hydroxide ions to them. So, with that in mind, we've got a general equation here. And this is showing that if we have the general metal M in the complex MH2O6 plus 3 and we add an OH minus, it might look like a straightforward swap between an OH and an H2O. But remember what we saw previously. The OH minus is acting as a base. It's therefore acting as a proton acceptor. The complex is acting as a proton donor. So one of the H2Os is donating a proton to the OH minus to make the H2O. But if I added a second hydroxide ion, what would it look like? Well, we start with what we made in the first equation, my MH2O5OH. It's gone down to +2 because the OH has a minus charge, and we're adding a second OH minus to it. Now, that OH minus is going to take another proton from the complex. So that's going to take it down to H2O4OH2. The charge at that point will be, it's gone down from +2 to +1. And I'm going to add the state symbol in there. That one is aqueous. And in doing so, the OH minus accepting a proton has made another H2O. Now it's asking you to take a look at what would happen if another hydroxide ion was added. So let's have a look at that one now. Again, I take what I made here, I move it down, and I am going to make my complex. This time, instead of H2O4OH2, it's H2O3OH3. I still make a water ligand. Something really important to think about here is the state symbol. What state would this be in? And hopefully what you have said is solid. And I've highlighted that there. And we're going to talk a little bit about why. First of all, why might this mean that the reaction stops? And the complex is no longer dissolved in solution. It's now solid. It's precipitated out of the solution. Why is that? Well, we know that ionic compounds dissolve in water. This is no longer an ionic compound. This has got dated covalent bonds between the M and the H2O and M and the OHs, and doesn't have an overall charge. So because it's precipitated out, it can no longer continue to react. So now let's have a think about what would happen if instead of MH2O6 plus 3, we started with MH2O6 plus 2. Have a go at writing all of the relevant equations for this one. So, in the first instance, we've got MH2O6 plus 2, that's aqueous. We're adding OH minus, that's aqueous. And that OH minus is going to take a proton, which means that one of the H2Os in the complex becomes OH. We have H2O5 OH. That's a -1 charge. The M is +2, so overall the complex has a charge of +1. And obviously I need to include the H2O that I've made. If I then take my MH2O5OH plus and I add another OH minus, at this point I make MH2O4OH2, but just as we saw earlier, that now has 0 charge. That means it can no longer dissolve. And that means that it's solid. That has precipitated out of solution. Incidentally, there are observations you're going to have to learn for all of these reactions, and we're going to talk about those in the final video of this topic. Obviously, we need to include the H2O there as well. Now, there is an alternative here that you might be asked to write the overall equation. You could have been asked to do that with the +3 ion as well. What would this look like overall? Well, we're starting with our H2O6 plus 2, but I'm adding 2 OH minuses because I added one to make this and another one to make this. That's going to take me to my final complex, MH2O4 OH2, solid, no charge, and that means that in doing so we have made 2H2O. So always read the question carefully. These reactions do happen stepwise. You might be asked for individual steps, but you may be asked to do the whole thing from beginning to end. With that in mind, there are lots of examples here for you to try to really cement that idea and help you to reinforce what you need to know. So, copper H2O6 plus 2, if we add an OH minus, it's going to go down to H2O5 OH. It's still positive, charge has gone down by 1. That means it's aqueous because it has a charge, and we make 1 H2O. Very similar idea on the next one. We're going to Fe H2O5 OH plus, that's aqueous, and we're adding water, and we're making water, which is a liquid. If we do this with Fe H2O6 plus 3, and we add OH minus, it looks almost identical to the example above. The only difference is the charge has gone down to plus 2. And going down to the final example of adding 1 OH minus, this looks more like the top two. The COH2O5 OH goes down to a plus charge because OH is minus 1, and we make 1 water, which is liquid. The following 3 examples, we're adding more than 1 OH minus. This is not stepwise reactions. So, in this case, adding 2 OH minuses, we're going to end up with H2O4 OH2. We're remembering because that has no charge, that's now solid. And because we added 2 OH minus and liberated 2 hydrogen ions, that means we've made 2 H2O liquid. Very similar idea with the next one, Fe H2O4 OH2, solid, no charge, and 2 H2O. We've then got Fe H2O6 plus 3. Now, we could add 3 OH minus in total here, as we saw previously, but we're only being asked to add 2. So, we are going to go to H2O4 OH2, but that will still be plus 1. 2 OH minuses with an Fe plus 3 means an overall charge of plus 1. Because it's charged, that means it has a state symbol, it's aqueous. And again, because we added 2 OH minus, that means we've got 2 H2O. Let's also take a look at the reactions with carbonate ions. These are very different when we have complexes with plus 3 metal ions and when they have plus 2 metal ions. And we're going to look at both of them. But to begin on this section, we're going to go back to way before A level. And I'd like to have a think about the general equation for when we add an acid to a metal carbonate. And an acid plus a metal carbonate goes on to make a salt, goes on to make water, but it also goes on to make carbon dioxide. And we can use this as a test for carboxylic acids. So what would we do? What would we add? What would we observe? Well, in the first instance, you would add a metal carbonate to the substance being tested, the substance you think might be a carboxylic acid. If there's no effervescence, it's not a carboxylic acid, but if it does effervesce, you would collect that gas and bubble it through lime water. And if we wanted to prove that it was definitely, decisively a carboxylic acid, we would be looking for the lime water to go cloudy. Now that's pre-A level, but still incredibly relevant to what we need to know now as well. So let's now have a think about the reactions that are taking place. Again, we have got a general equation up here. I am going to correct it. That should have 3 HCO3 minus. And I've also added the little state symbol here. This is solid because this complex now has no charge. But with this general equation in mind, have a go at writing out the equations where the same thing happens with the following complexes. Well, the 3CO3 minus means that we're going to end up with 3HCO3, or CO3 minus, sorry. Each of those takes an H plus. That makes 3HCO3 minus. We make our complex, FeH2O3OH3, no charge, so it's solid. Similar idea with cobalt, you can see there. And a similar idea with chromium. But this might be standing out as being a little bit odd, because we've just spoken about what happens when acids are added to metal carbonates. We know that that will produce CO2. We know that would cause effervescence. But according to this, there is no effervescence. So we need to unpick why. Now, this is the actual equation. You could be asked to replicate this for a given complex. This would always be the case for a metal complex with a +3 central metal ion. So what would this equation look like using FeH2O6 plus 3 properly balanced? Well, I've got one of the complex and one of the product complex. I am going to need to add 3 CO3 minus if I'm going to remove 3 of the H pluses. And if I remove 3 of the H pluses, I do end up making HCO3 minus, but it breaks down into CO2 and H2O. I now need to add the state symbols. I've got my aqueous carbonate ions, I've got my gaseous carbon dioxide, and my liquid water. Now, have a read through this and try and answer the questions that follow. Because this is showing what's actually happening here. When we talk about HCO3 minus ions, that's an H plus with a CO3 minus. This is what's actually happening. H3O plus ions are reacting with CO3 minus ions to make water and carbon dioxide. So where is the H3O plus coming from in the first equation? Well, we know, as I've already said, HCO3 minus is a combination of H plus and CO3 minus, but we know that H plus ions don't really exist. That is going to be an H3O plus ion. The H plus is going to be combining with water. And that then allows us to see how the H3O plus and CO3 minus can break down to give us water and to give us carbon dioxide, the effervescence that we would see, that we could bubble through lime water, that would go cloudy, proving the acidic nature of this complex. Which way would the equilibrium shift if the H3O plus is used up? Well, it's going to shift to the right. And why is that? We're going back to actually GCSE equilibrium knowledge here. It's because if you decrease the H3O plus concentration, the system will act to oppose that change. It will try to increase it by favouring the forward reaction and shifting the equilibrium to the right. Now, when we consider carbonate ions with +2 complexes, this is an entirely different scenario. Have a think about these questions. So, H2O6 plus 2, that's less acidic than FeH2O6 plus 3. And I'm going to say that if you're not sure about why, go back to video 1 in this topic, because that goes through all of the details as much as you will need to know. What would the formula of iron 2 carbonate be? Well, there's a reliance here on you knowing that carbonate CO3 has a -2 charge, but also knowing that this 2 in brackets tells us that the ion has a charge of +2. So if Fe is +2 and CO3 is -2, you need one of each of them to get a balanced formula. So the formula is FeCO3. So this is what actually happens when you react a +2 ion complex, any +2 ion complex with carbonate ions. We don't get the effervescence, we don't get all of that additional difficulty that we saw in the previous ones. We simply make the metal carbonate, MCO3, and all of the water ligands are lost. So what will the equations look like in this case? Well, in this case, I'm going to make FeCO3. From copper, I'll make CuCO3. From cobalt, I'll make CoCO3. And in all of those cases, all of the water ligands are lost, so we get 6H2O. There is a possible link here in questions to entropy, because what you can see is a huge increase in entropy here. We've gone from 2 moles to 7 moles in each case. So just be prepared for a little bit of thermodynamics to find its way into these questions. Okay, a little bit here on distinguishing between iron 2 and iron 3 ions. This is a key practical that you will need to remember the details, how to do it, and what you would observe. If I take an iron 2 solution and an iron 3 solution, it could be quite difficult to distinguish between them. I'll talk about why in a moment. But if I add sodium hydroxide, we've already spoken about the fact that that reaction will carry on until a solid precipitates out. So if I add sodium hydroxide to iron 2, I will get my pale green solution. We're going to talk about these colours and these observations in the final video a lot more, but I'll actually make a green precipitate, a green solid. If I take iron 3, I've got plus 3 ions, that's a pale brown solution, and I'm going to end up making a brown precipitate. Now, why is this useful? If I've got a very dilute solution containing either iron 2 or iron 3, it might be pale green or it might be pale brown, but it might be very hard for me to distinguish between them. But if I precipitate them out, the colours become a lot more vivid. It makes it much easier to distinguish. Okay, we're going to finish off by looking at further addition of hydroxide ions. We're going to look at amphoteric hydroxides. There's a specific metal hydroxide that's amphoteric that you need to learn about, and that's aluminium. But have a think about these questions and then we'll review. So this is after I've added OH minus. I've made my complex. What state will this complex be in? It will be solid. It will be solid. Why? Because it has no charge anymore, so it won't dissolve in water. Now have a think about what would happen if you took this complex and you added 3 moles of HCl. What do you think would happen? Well, there's the beginning of my equation, my complex that I started with here, H2O3OH3, and I'm adding HCl. Now the HCl is going to act as an acid. It's going to be a proton donor. So it's going to donate protons to the 3 OHs, taking them back to H2O. Because H2O has 0 charge, aluminium has a plus 3 charge, we're also going to regenerate that plus 3 charge on the complex, making it charged, which means it will dissolve in water, making the state symbol aqueous. And in doing so, I am going to be left with my 3 Cl minuses. They've donated their protons, they're left as chloride ions. What is the complex acting as? Well, the acid, hydrochloric acid, is acting as an acid. It's donating protons. The complex has accepted protons. So that means it's acting as a base. Now let's think about what would happen if I took that complex and I added 1 more mole of hydroxide ions. Because although that doesn't commonly happen, it can happen in this specific circumstance. Well, you could end up with that OH minus taking an extra proton, taking us to H2O2, OH4. I've now got a charge again. That's -1. That means it's redissolved. It was a precipitate, but that precipitate has redissolved into the solution. And I've got my H2O that I made. So in this case, the complex that we began with is donating a proton, and that means it's acting as an acid. And that takes us to that reminder that when we talk about something being amphoteric, it can act as an acid and it can act as a base. That takes us to the end of this video. Thank you for listening and goodbye.